I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we'll see the example problem for GIL clumping algorithm. The GIL clumping algorithm is a local search optimization technique used in AI to find the best possible solution by iteratively improving a candidate solution. It starts with an arbitrary solution and moves to a neighboring solution with a higher value based on a given evaluation function. The process continues until no better neighboring solution is found, leading to a local optimum. However, it may get stuck in local maxima, plates, or ridges, making it less effective for complex problems. Variants like simulator annealing and stochastic gill clumping help overcome these limitations. First, we will see the gill clumping algorithm. In this gill clumping algorithm, we'll see the detailed explanation in this slide. We'll see to it. Gill clumping is a local search algorithm used in optimization problem where global where a goal is to find the best possible solution by iteratively improving the current state. The algorithm starts with an initial solution and continuously moves toward a better solution by evaluating neighbor states. It always selects the neighbor with the highest value, similar to a clumper, always moves uphill to reach the highest peak in a landscape. This method is widely used in machine learning, robotics, scheduling, and game AI as it provides a simple and effective way to solve optimization problems. However, this gill clumping has some limitations. What I've said, it can stuck in local maxima, plates, or edges, which may prevent it from reaching the global best solution. Variants like steepest ascent, first choice, or stochastic gill clumping are used to overcome these challenges and improve search efficiency. Next, we'll see the working principles and termination condition. Uh, the gill clumping algorithm's working condition we'll see step by step. Gill clumping is a local search optimization. Discuss. It begins with the randomly chosen initial solution. The algorithm then evaluates its neighboring solution to determine which one has the highest value according to the objective function. If a neighboring state offers a better value than the current state, the algorithm moves to that neighbor and continues the search. This process is repeated iteratively with the algorithm always selecting the best available neighbor until it reaches a point where no better neighbor exists. At this stage, the algorithm terminates and solution obtained is considered a peak. This peak can either be a local maximum where a better solution exists elsewhere in the search space or global maximum, the better or best possible solution. This global maxima, we are calling it as best possible solution. Due to its greedy nature, gill clumping stuck in local optima, plates, or ridges, which may prevent it from finding the absolute best solution. And what is the termination conditions of this algorithm? The termination condition of the gill clumping algorithm has been founded by the gill clumping algorithm stops when one of the following conditions. A peak is reached. Peak is reached. The algorithm stops when it finds the state where none of the neighboring state have higher value. This peak could be a local maxima or a good but not the best solution, or global maxima, the best possible solution. Since gill clumping only moves to better states, it cannot escape local maxima without modifications like random restarts or simulated annealing. Next, a predefined number of iterations is completed. No? In some cases, the algorithm is set to run for a fixed number of iterations or until a time limit is reached. This is useful when the search space is large or when an appropriate solution is acceptable instead of the absolute best solution. Next, the improvement in value is negligible. If the changes in the solution's value becomes insignificant or very small over multiple iterations, the algorithms may stop early. This prevents unnecessary computations when further improvements are minimal and ensures efficiency in practical applications. These termination conditions helps control the search process and prevent the algorithm from running indefinitely while ensuring a balance between efficiency and accuracy in finding an optimal or near optimal solutions. And the additional key features of gill clumping algorithms are it also called the greedy local search. How means it is because it focuses solely on the selecting the best immediate neighbor without considering the future consequences. This greedy nature makes it efficient but also increases the likelihood of getting trapped in local maxima, plates, or ridges. Each node in the grid clumping algorithm consists of two essential components. What are all the two essential components? State and value. The state represents the specific configuration. Specific configurations in a search space, while the value is the objective functions. Objective functions evaluation for that state. The algorithm uses these values to determine the best possible move at each step. And gill clumping is most effective when a well defined heuristic function is available, guiding the nature toward a better solution quickly. And unlike global search methods, gill clumping does not require maintaining an entire search tree or graph. Instead, it keeps track of only the current state, making it memory efficient and suitable for solving the large space optimal problems. And the characteristics of gill clumping algorithms are gill clumping is a variant of generate and test method where the algorithm continuously generate and test variant. It continuously generates new states and evaluates them to determine the best possible move. The key difference is that in gill clumping, feedback from previous evaluations helps decide the search direction, ensuring that the algorithm progresses toward an optimal solution rather than exploring randomly. This algorithm follows a greedy approach, meaning it always moves toward the immediate best neighbor that optimizes the objective function or reduces the cost. By making locally optimal choices at each step, it efficiently finds better solutions, although it may not always reach a global optimal. Once the significant characteristics of is that it does not support, this will never support the backtracking as it does not retain memory of previous states. Memory is not available, it will not go for the backtracking. This lack of memory helps in reducing computational overhead but also makes the algorithm prone to getting stuck at local maxima, plates, ridges where no immediate better move exists. Next, we'll see the one example problem by using the state space, gill clumping state space diagram. The state space diagram in gill clumping represents the landscape of possible solutions where each state corresponds to a potential solution and objective function value determines its elevation. Here, the x-axis represents the different states while the y-axis represents the objective function or objective function or cost function value. The cost function, we can say that the goal of the algorithm is to navigate this landscape and reach the global maximum. This is the best solution. Global maximum, that is the highest peak. Highest peak when the maximizing a further or a global minimum, that is lowest point, and minimizing a function. However, due to its greedy nature, guild climbing may get stuck at local maxima, plates, or ridges, making it important to use variations like random state charts, simulated annealing to escape suboptimal solutions. So as I've said, the state diagram. It is the about this diagram is the visual representation of what possible states the search algorithm can explore. And the objective is what is the objective of this state space diagram? To find the state where the optimal objective function reaches is the maximum value. This maximum value we are calling it as the global maximum. In x-axis, this x-axis represents what? State space, and y-axis represents the objective function or cost function. Represents the value of objective function corresponding to each state. And here we are finding out the six terminologies from this graph. The terminologies we'll see one by one. The first one is the local maxima. Here, it is the local. This one is the local maxima. What does local maxima represents? It is the peak in that state landscape that is higher than its neighboring state but lower than the global maxima. Local maxima, if you are considering, this value is the higher than that of the neighboring value but lesser than that of this global maxima. The algorithm may stuck here if it does not explore beyond the next immediate neighbors. If it has not been explored, it will be stucking over in this maximum. Local maxima. Next, global maxima. This global maxima is the highest peak. Here, this is the highest peak value in the entire landscape. It represents the best possible solution where the objective function reaches its maximum value. Next, current state. Here, the current state may start over here. The current state represents it's the position of the algorithm at any given point in the search space. This algorithm moves from this state to better neighboring state during the search space. Next, ridges. So ridges, what it says that this ridges we can say it as a higher region in the slope which can look like a peak. This it will be looking like a peak. This may cause the algorithm to stop prematurely, missing better solution nearby. Next, flat local maxima. Flat local maxima. Here, this is the flat local maxima. We can call it as flat local maxima, flat region. A flat local maxima is the region where multiple neighboring states have the same value. Why it is same value? It is flat region. So from here to here it will have a same value as the current state. This can make it difficult for algorithm to decide which direction to move next, whether this side or this side. It is very difficult to analyze. Next is shoulder. This shoulder, the shoulder, it represents, this is such a flatter, is a plateau with an uphill edge, allowing algorithm to move toward better solution if it continues searching beyond the plate. Here, this algorithm, it is allowing the algorithm to search in the upward to find out the global value, global maximum value. So the example we'll consider over here is the NQN problem. So put NQNs on the, if I am considering the 4 cross 4 chessboard, if I am taking, I'll have 4 rows and 4 columns. That we can call it as N cross N board with no two queues on the same row, column and diagonal. You know the function of the queue, it can move into either horizontal or horizontal or vertical or a diagonal. It can move in three directions: row, column and diagonal. Move a queue to reduce the number of conflicts. So if it has been in the same row or same diagonal or the same column, we have to move upward or downward, to reduce the conflicts. So here we have to find out the cost function in the end. So in the guild clumping algorithm, cost refers to the evaluation function, that is the heuristic function used to measure how a good solution is. In the NQN problem, the cost is typically defined as the number of attacking pairs. If two queues are present, here one queue, here one queue, horizontally it will be attacking, or here it is present, it is that is diagonally it will be attacking, here the horizontally it will be attacking. This is what we are saying. In the n-queue problem, the cost is typically defined as the number of attacking pairs of the queues. The cost in the n-queue, a lower cost is better, that is cost should be equal to 0. And cost function, the number of pairs queues attacking each other, how row wise, column wise, or diagonal. This is possible for the queues. The algorithm moves to a neighboring state with a lower cost to a minimum attacks. We'll see one example problem. So here this is the 4 cross 4 queue problem. Here 4 queues are placed. This first queue is placed in the third row, first column. Second queue is placed in the second row, second column. And the third row is placed in the second row and the fourth column. And this queue is placed in the third row and fourth column. Here, how many stacks are there? 1, 2, diagonal, here horizontal and diagonal. So, what is the heuristic value here? 5. And if I am moving this queue upward by one step, here I am reducing the stack. 1, 2. Here there is no diagonal. Here it is not possible to hit this queue by this queue. So the h value is equal to 2 here. Again, what I am doing is I am moving downward of this queue. Here it is the original one. So if you are considering there is no diagonal for this, no horizontal, and here there is no diagonal, hit is there, and here there is no horizontal. So h value is 0. So after the second iteration, here this is iteration 1 and this is iteration 2. In the second iteration, we are getting the cost function. H value is 0. And this is the example problem for 8 cross 8 cube. Just have finally the solved problem I have taken it from some other book. Here there's no stuck for this, there's no stuck for this, and only cases this is only being stuck with each other. Here there's no stuck at all, there's no stuck at all for this cube. Similarly, so what is the local minimum value? The h value is equal to 1. Only one position it is hitting with each other. So in this way, we are going to find out the cost function or a heuristic function. So the main advantages of the local search algorithm, it uses the less memory and it is used to find out the reasonable solution in large infinite spaces. Hope all you have enjoyed the example problem of glue glimping. The remaining things we'll discuss in the next lecture. Thank you.